Okay, so let's quickly start off with this week. Sorry, I was a bit late. Not gonna lie, I'm a bit behind on my studies. Uni finals got me. So let's go over this week. I want to cover the factors that would affect equilibrium. Okay, and you'll need to know in a few things about equilibrium. Um, let's just cover the topic. Equilibrium. We know Le Chatelier's principle. And number two is collision theory. How does collision theory affect equilibrium? Okay, let us see. So let's talk about number one first. What does Le Chatelier's principle do? Okay, what does, oh my goodness, why does that happen? Okay, Le Chatelier's, what does it mean? Okay, so I'm not going to write this down, and I'll expect you to actually listen to my lectures so you can annotate it, because it'll take me too long. So Le Chatelier's principle, the purpose of this once again is a predictive agent. It helps us guess if an equation or a reaction would proceed to the left or to the right. Okay, so left or right. Okay, and what that means is which side would be upregulated. Okay. And in this case, we talked about several things, but it is very important for you to understand that this sign is used in equilibrium reactions. Okay, it means it can go this way and it can go this way. Okay, very simple. You know that, but it's sometimes even I forget. Okay. Um. Okay, and also one more thing. This happens in dynamic equilibrium. Okay. I want you to recall what dynamic versus a static equilibrium is, because dynamic equilibrium means both sides are changing and it is reversible. Okay, reversible. Okay, these are all key terms I want you to chuck in to one of your short answer responses. Okay, let me see my notes. Okay, so today we'll be using these two concepts to explain Le Chatelier's principle, and it is when there is a disturbance in a closed system after affecting its equilibrium position. Okay, what does that mean to you? Do you remember what we talked about disturbance in a closed system? A closed system, FYI, is like a Coke can. Okay, you can't really see anything outside. You can't go inside. It is fully enclosed. So imagine it was a perfect Coke can. There was titanium, and in the middle here, where there in this imaginary Coke can, there is no heat transfer out or heat transfer in. Okay, so it's just this little space. Okay, and this is all theoretical so far, but we will try to minimize any extraneous variables to help predict and bridge the gap between theoretical and experimental. So, the Chatelier's principle, what it does is it talks how a system, which is this closed system, will counteract the change by shifting equilibrium positions to minimize the effects of disturbance. So, the Chatelier's principle, it predicts that a system counteracts. I'm gonna just write the counteract change. Okay, change. Um, shift it by shifting equilibrium for least. Okay, least disturbance. Okay, so that's very important. It will be least disturbance. Okay. Um, and once again, this only happens to closed systems, as we said. I'll emphasize that because in an open system, you can't really examine these effects, and there will be too many factors that will affect the reaction. So let us talk about the types of factors that can affect equilibrium. I'm pretty sure we talked about this. There's temperature, okay, there is concentration of substance, there is pressure, and there is volume. And recall that these two are related. There's also catalyst, which I didn't mention to you last time. But these would all affect how an equilibrium is established in a closed system, which can be predicted by Le Chatelier's principle. Okay, so let's talk about how temperature works. Remember, we use the Haber process for this, by the way, and I want you to recall the Haber process is a reaction between dinitrogen and hydrogen. Hydrogen, what is this? What are these? Remember, they're all gas. And I want you to take a second and predict um, what the products are of this reaction. Okay, I'm going to continue, but pause it and see if you can recall this. Um, really, this is the only reaction you really need to memorize for this topic. Let me get some ice cream, baby. So really try to memorize this equation, okay? Okay. Oh, that's good. Sorry, mint ice cream, really good. Haber process is, remember, is very important in what process? In producing this. And this is ammonia. Ammonia can be used in a lot of fertilizers, which has really evolutionized the agricultural industry in very socioeconomically low standardized economies, such as maybe developing Africa, which case this has radically changed the lives of people and given them the ability to grow crops in soil that was once low in nutrition. Okay, and we talked about this. Um, this heat. Why do we write heat? Well, remember we talked about delta H is this reaction exo or endothermic. Okay, is this exo or endothermic? And just write the heat on which side. So for example, this Haber reaction, we know, I think it was like delta H is equal to negative 81 kilojoules. I'm not sure, but I know it was negative, and if it's negative, it means that it lost energy, right? On this, it lost energy. So there's a little activation energy. Oops, activation energy. Sorry about that. EA here, and this is delta H, right? So it lost energy. Okay, this is H2 and N2. This is NH3. I don't know why there's little strands here. Sorry about that, but don't worry about that. That is just a rough energy diagram. We know that it is exothermic, so we write add heat here. Okay, add heat. Once again, it's because it's exothermic and we lose heat. It's not because it gains heat. No, no, no. It's the product is ammonia and heat. It's releasing heat, and in doing so, it's losing energy in the form of this. Okay, its internal energy is lost, and the heat is just a little trick that we used to help us understand how temperature affects equilibrium. If the forward reaction is endothermic, however, we would write heat on the other side. Okay, but in this case, we don't because it's exothermic. Good. Okay, so why do we add heat on that side? We say that the system's enthalpy, or the total internal energy, decreases, but the surrounding environment's enthalpy increases. Okay, so for exothermic reactions, the change in the system's enthalpy is negative, and the change in surrounding environment's enthalpy is positive. Does that make sense? It's negative internally, but you feel the heat on your fingers, right? So that's why we add heat. This means that ammonia and heat is released into the environment, okay? And hence our equation here. Great. So in general, we write it on the right side, right hand side if it's exothermic, and left hand side if it's endothermic, okay? Okay. Uh, let me see. Hmm. Okay, so back on how Le Chatelier's principle affects this. What this means is we can use Le Chatelier's to predict how this would work. For temperature, there would be two ways in which temperature can affect it, and we'll use the less thermodynamically accurate standpoint to talk about it first. Once again, if the right side produces heat, and we have heat being added, you should imagine that increasing the temperature will greatly disturb the right hand side more than the left hand side, and therefore the system will shift equilibrium to the left to counteract the disturbance in the right. Does that make sense? So if we were to add heat, so if we added heat temperature, fire, 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 fire. Okay, so ignore all of this. Let me rub this all out. If we added temperature, how it would affect both the forward and reverse reactions, but which one would be affected more? Probably this one, because it has added heat, right? And therefore, the Chateliers would shift equilibrium to that side, right? And this side will be upregulated to counteract this side because it has heat, okay? Because there'll be a greater disturbance on the right-hand side. Um, okay, and therefore the right-hand side, oh, sorry about that, that was my UE boo. Um, Therefore, the species on the right hand side of the reaction, which is the ammonia molecules, they'll react, and this will help to form more nitrogen and hydrogen gas. Hence, this is upregulated. This will be less prevalent. This NH3, right? Because of the heat, it's exothermic. So, adding temperature, Le Chatelier wants to decrease the disturbance. Makes sense, hopefully. So, let's say we remove heat. I add ice this time. Ice cube. Okay. Oh, super cold. And ice cube. Okay. What happens now? Can you tell me? This is the opposite process. So if you take away heat, heat is being taken away from the right hand side of the equation. And this leaves us with N2 plus 3H2 makes 2NH3 without heat. Okay, no heat this time. Okay, no heat. So this creates a disturbance in the system. So according to Le Chatelier's principle, the equilibrium system will shift to the right. Okay, why? To produce more heat, to counteract and minimize the change in the temperature. So this shift in the equilibrium position, the concentration of ammonia will increase, and the concentration of what is this? Nitrogen and hydrogen gas would decrease. Okay, and once again, why? If it shifts to that side, we know that it is NH3. Remember this products over this. Okay, that's very important. That and this has no units. Okay, no units. FYI, no units. Okay, so according to Le Chatelier's, it will shift to the right in order to counteract and produce more heat to minimize the change of adding ice cubes. Okay. Okay. Therefore, concentration of ammonia would increase, as we said, and this would decrease. Great. So let's talk about this more accurately. What would happen? Well, since the reverse reaction of the Haber process is endothermic, the equilibrium position will shift to the left-hand side in favor of the endothermic reaction to consume less heat inputted into the system to counteract and minimize the increase in temperature. And if the temperature of the system decreases, then the forward reaction of the Haber process is exothermic, you know that. So the equilibrium position will shift to the right hand side in favor of the exothermic reaction to produce more heat to counteract and minimize the drop in temperature. And we talked about this in the less accurate and the more accurate. Okay, great. Okay. I think that is all I have for temperature. Let's talk about concentration, okay? How can the Chatelier's principle be used to talk about concentration? Okay, how? Well, this is 13 minutes already. I'm gonna wrap this. I know, I never had that much energy when I was in your age. So let's quickly talk about this. I don't want you to listen to a whole lecture for like 30 minutes. We talked about how this was N2 plus 3H2 makes 2NH3 plus heat, okay? And we increase the concentration of ammonia by pumping more ammonia into the system. What will happen? We predict that the equation will shift to the left, okay? Why? According to Le Chatelier's principle, the disturbance experienced by the system will be an increase in the concentration of NH3, right? So to counteract and minimize the disturbance, the system will shift its equilibrium to the left to decrease the NH3, which means that the N2 and H2 will increase. Okay? Does that make sense to you? So if we increase the concentration of ammonia, we'll produce more nitrogen and hydrogen to counteract the effects of this growing. Okay? Does that make sense? Which means that the concentrations of nitrogen and hydrogen will increase. Okay. This also depends on the molar ratio, which is 1 to 3 to 2. Okay. Let's see. And same. If you pump more nitrogen or hydrogen into the system, there will be an increase in concentration. Therefore, it will shift to the right, as per Le Chatelier's, to counteract and minimize the increase in nitrogen and hydrogen gas concentrations, and it will increase in ammonia concentration. This helps to reestablish the equilibrium, and equilibrium will be reestablished. Yes. This one was much easier. And it's much more complicated for liquids, and we don't really talk about it for solids. But for liquids, depends on how they act. Solvent, solute. But in gases, it's pretty simple. Okay, let's talk about changes in pressure. And pressure sounds like what? Gas pressure, right? Pressure. Only gas, okay? Gas, 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 okay? It doesn't no effect on solids or liquids, okay? Okay, so let's talk about the moles of gases on each side of the chemical reaction, and this helps us predict the direction of the equilibrium shift when the system's pressure changes. So the Haber process once again, plus 3H2 makes, sorry, my friend's calling me, I'll cancel his call. 3H2 makes 2NH3 plus heat. Okay, you know this. There are 4 moles of gas on the right hand side. We talked about this molar ratio, 1, 2, 3 to 2, right? This is 4, and there's 2 here. Okay, great. Um, and this means that nitrogen and hydrogen collectively exert more pressure than ammonia molecules on the system, right? So if there is an increase in the pressure, the system will shift its equilibrium to the side with the least moles of gas, to the right. Does that make sense? So if we increase the pressure, this side will be upregulated. More of this will be produced. Equilibrium shift to the right. And because the left side is much more affected than the right side, as you can see by the molar ratios, right? This will counteract and minimize the increase in pressure. Let's see. So likewise, if there is a decrease in pressure, the equilibrium will shift to the left side because there is a greater drop to the left side because of the molar ratios, and hence this will help counteract and minimize the decrease in pressure. Let us talk about the changes in volume then. Okay, so last but not least, we'll talk about catalysts in a bit. Volume, very similar to concentration, not very difficult though. This one is, I would say, easier. Once again, it will have no effect on liquids or gases. No, it has effects on gases, on solids. Let us talk about it. So we also need the moles of gases on each side when we talk about volume. Do you know why? We talked about how gas and volume and pressure is interrelated. We have 4 moles of gas on the left hand side. We have 2 mole on the RHS. So if the volume increases, what does that mean? Okay, what does that mean if the volume increases? Obviously, there is not newly introduced species into the system, so pressure decreases, right? Because there is more space. Imagine it was like this before. Now it's like this. There's still 3 balls. Okay, and pressure is defined as how much force is exerted by each molecule on the container. Not much force anymore because there's not much more pressure. There's not much more incentive for these molecules to be pushing in and out of each other because there's less collisions, right? There is therefore much more room for the particles to move, so you can think about it having less time colliding with the walls of the container because there is greater distance, right? Because it increased the volume. So if the volume of the system increases, there will be a decrease in pressure. The equilibrium will shift to the side of the chemical equilibrium with more moles of gas to counteract and minimize the decrease in pressure. So it will shift to the left if the volume increases, okay? Because there is more moles of gas, right? And it wants to minimize the decrease in pressure, okay? So if, let me think about this. How would I write this? If volume increases of gas, Kc will shift to the left. Why? Because there's 4 moles of gas, right? And there will be a drastic drop in pressure if we do not shift to the left hand side. Okay. What else do I need to talk about? Nope. And quickly, I'll just talk about the inverse relationship between pressure and volume. I'm pretty sure you know what Boyle's law is. P1 V1 is equal to P2 V2. I never get them right. Charles law, Gay-Lussac's law, Boyle's law, Newton's physics. No. But there is an inverse relationship, and it's very evident. You know, if P1 is 3, V1 is 2, is equal to, let's say, like 6 and 1, right? If we increase this to make, let's say, 4, and this is the same, obviously volume would have to decrease, right? It would have to decrease to like 4 times 1.5, right? So volume decreases when pressure increases, and we call that inversely proportional. Okay, good. Let me see. In terms of collision theory, I mentioned it's very necessary for us to talk about, but I don't have notes on that, so I'm gonna make notes for you now. If you want, let me see. Yep, I'm gonna end this one quickly and upload this for you. Collision theory has a formula. Before I end, I want to see if you can understand this. Okay. And this is called the Arrhenius theory, actually. The Arrhenius reaction. You'll notice that a lot of these are this is activation energy, and you see this in the perfect gas law, right? What else is there? This is the Arrhenius equation, and it's used to determine this. Do you know what that is? Rate constant. Yeah, great. So let's talk about equilibrium reactions, and the rate of the reaction going forward and backwards, right? So yeah. Okay, so I think for your purposes, that is most important right now. And I noticed that you said you have ions, right? We'll talk about how to name ions and solubility. I'll make that before we have our class on Saturday.